Let's look at how to find horizontal and vertical intercepts, asymptotes, and then use those features to sketch a graph of our function. So starting out, looking at our function g of x, let's look at intercepts first. So to find a vertical intercept, finding the point where this graph crosses the vertical axis, when we're finding vertical intercepts, this is where we always think about doing an evaluate. We're going to plug in 0 for x and evaluate our function. So g of 0 is equal to 0 plus 2 times 0 plus 1 over 0 minus 1. So we have 2 times 1 over negative 1, which is equal to negative 2. So remember, intercepts are points on the graph. So this is an ordered pair. This is the point 0, negative 2. So a vertical intercept we evaluate. That means to find a horizontal intercept, this is where we're going to solve. So what we're going to do is we're going to take our function and set it equal to 0. So we're thinking about when is g of x equal to 0. So when is x plus 2 over x plus 1 all over x minus 1 equal to 0. Now, if we were to multiply each side by x minus 1 to get rid of the fractions, we're still left with our x plus 2 and x plus 1 on the left-hand side, and 0 times x minus 1 is just 0. So really, when we're finding horizontal intercepts of a rational function, it's always going to be just setting our numerator equal to 0. Set each of these factors equal to 0 and solve for x. So we have two values of x. This corresponds to two horizontal intercepts. So we have the point negative 2, 0, and the points negative 1, 0. So we have our horizontal and vertical intercepts. Now let's switch over to horizontal and vertical asymptotes. So as we're thinking about a vertical asymptote, this is where we look at our denominator of our function and set it equal to 0. So x minus 1 equal to 0, we get x equals 1. So remember, this is an equation of a vertical line. This is an x value where our function does not exist. But as the function approaches x equals 1 on the graph, the tails will be going either up to positive infinity or down to negative infinity. Now let's think about horizontal. When we're thinking about horizontal asymptotes, this is where we take a look at the degree of the function. It may be helpful here to actually multiply out your numerator. So if we were to FOIL x plus 2 times x plus 1, we'd have x squared plus 1x plus 2x, so we could write that as plus 3x plus 2 all over x minus 1. So we're always looking at the leading terms so that we can find the degree when we're thinking about horizontal asymptotes. So this function has a degree 2 in the numerator and a degree of 1 in the denominator. So this is one where the denominator is less than the numerator. When that happens, there is no horizontal asymptote. So this is telling us that the tails of our graph do not flatten out along a horizontal line. But when there is no horizontal asymptote, then we want to do one additional step and look for an oblique asymptote or a slanted asymptote. So to find our equation, we need to do division, either long division or synthetic division. Here, since our denominator is in the form x minus 1, we can do synthetic division. So I'm going to put a positive 1 out in front, and then my coefficients 1, 3, and 2 underneath. Bring down the 1 and then multiply, add. 1 times 1 is 1, 3 plus 1 is 4, 1 times 4 is 4, 2 plus 4 is 6. Ignore the remainder, so we don't use this part at all when we're doing our equation of our oblique asymptote. And these values are giving you the coefficients for your equation of your oblique asymptote. So it's going to be the line y equals, so it's an equation, just like our vertical asymptote is an equation. The 1 is the coefficient on your x, and the 4 is a constant term. So 1x plus 4, or just x plus 4. Now let's take all this information and create a graph. let's start by marking all the information that we had already found on our graph. So starting with our points, our vertical intercept is the point 0, -2. Our horizontal intercepts are at -2, 0 and -1, 0. We have a vertical asymptote at the line x equals 1, so it's a vertical line. And then our oblique asymptote y equals x plus 4. So think of this in y equals mx plus b form. This is a slope of 1 and a y-intercept of 4. So starting at 4, it goes up 1 and right 1, up 1 and right 1 using our slope. So this has sectioned our graph into a couple of pieces. On the left side of our vertical asymptote, we have 3 points, and so that's probably enough that we can start to sketch in the shape of our graph. We know that our graph is going to follow down here to -infinity, and then it's going to follow along our slanted or our oblique asymptote on the other side. So as it approaches x equals 1, since all of our points were down below the slant asymptote, we can see that it's going to stay down below. And so as it approaches 1, it goes down to -infinity, and then the left side, that long run behavior, is that it follows along our slanted or our oblique asymptote. On the right-hand side of our vertical asymptote, we don't have any points marked on our graph because we don't have any intercepts on that side. So it might be helpful here to find an additional point just to have some idea where exactly to mark on our graph. So for example, if we were to evaluate our function at g of 3, so 3 is on the right side of our oblique asymptote. So g of 3 would be 3 plus 2 times 3 plus 1 all over 3 minus 1. So 5 times 4 all over 2, so 20 over 2 is equal to 10. So this gives us some idea. So g of 3 equals 10. There's an additional point that's up on our graph. So we know that it's up above our slanted or oblique asymptote, and so as it approaches x equals 1 from the left-hand side, it's going to go up to +infinity, and then as it goes off to the right, it needs to follow along our slanted asymptote. So using our point, we can start to fill in a general shape here, which for a sketch, that's all that we're really going for. You can take a look at this graph on your calculator. You may want to adjust your window a little bit as well, or graph it on Desmos.com.